audio. Ah, you can hear me now, right? Yes, thank you, thank you, thank you, thank you, thank you, thank you. Okay, good, good. Excelente. Excelente, Clemente. So, I was going through some stuff here the other day, and it occurred to me that there is a trick sort of hidden in the in the uh, uh, in the weeds here, which is that there's basically 3 points in any given titration where you're going to be asked to calculate the titrant concentration or the analyte concentration. And so I summarized these for everybody. And let's see here. So I have, let's see. There we go. That's what I'm looking for. I have, for titration calculations, I have A plus MT goes to products, right, whatever they are. And normally there's an equilibrium there, right? And A is analyte. T is titrant. V is volume. And so like there's VE, which is the endpoint or equivalence volume. Using those words interchangeably right now. And then there's VT, obviously, is the titrant volume. VA is the analyte volume. And then, there we go. So A is analyte, T is the titrant, right? So let's just say that let's just sort of define some of these things here. In this case, right? Actually, let me go up a couple. Where do we define this guy? Right. So here we got 25 mils of 0.04132 molar mercurous nitrate titrated with potassium iodate. Okay, let's see here. 25.00 mLs of 0.04132 molar Hg2 NO3 2 titrated with 0.05789 molar KiO3. And then the titration goes as Hg2 2 plus 2 iodates makes Hg2IO3 to solid, right? And we know KSP here, for example, KSP is equal to 1.3 times 10 to the minus 18. And we are supposed to find the Hg2 2 plus concentration, Hg2 2 plus at 3 points here, 34 mils at VE, whatever that is, and at 36 mils. Okay, so let's just go ahead and do this using our rules that we're going to make up here, right? Here's what I just said here. Titration calculations, analyte plus some number of titrant molecules makes a product. N could, maybe I need something by the A, but not perfectly generalized yet, but here we go. A is for analyte, T is for titrant. V is for volume, VE is equivalence volume, VT is titrant volume, VA is analyte volume. So in this setup here, VA is equal to what? VA is equal to 25.00 milliliters. CA, which is odd that we know this right now, but okay, is 0.04132 molar Hg2 NO3. CT is also known, concentration of the titrant. That's 0.05789 molar AiO3, right? And we need to know this, the conditions at 3 points. Pre-titrate, pre-endpoint, and at the pre-endpoint, Mr. Harris has gone to great pains to explain to us that the analyte concentration is equal to VE minus VT over VE times CA times VA over VA plus VT. Okay, so let's break this down here. VE minus VT over VE, this is the fraction of titrant remaining. Before VE, right? So, like, let's say if we've got, if it's going to be 50 mils, the VE is going to be 50 mils, and we're at 49 mils, then 50 minus 49 is 1 mil divided by 50. 1/50th, that's how much farther we have to go, right? Then concentration of analyte here is just whatever this guy is, right? That's the thing that we're titrating into, right? The analyte. And then VA is 25 mils, right? And there's 25 plus VT. So VT here might be 49, right? You know, so it's 25 over 25 plus 49. So this is how much remains. This is the concentration. And this is the dilution factor for that. So anyway, that one works, right? Then there's, let's make B post endpoint. And that guy here, now here we're actually going to solve for titrant first. And because when you do this experiment, right, before the endpoint, in the flask that you're titrating into, you have excess analyte. It's like you're say you're using up the acid and you're adding a little base, little base, little base, right? And then at a certain point, oh, you've added and up to that point, you haven't completely titrated the analyte, the acid, right? So you have excess acid, right? So this is excess A or analyte, or I don't know, acid in this case, right? And then post endpoint, you've used up all the A and you have extra T, right? So that one is actually fairly easy to calculate, right? And that's equal to the titrant concentration times VT minus VE. That's how many mils above the endpoint you've gone, divided by VA plus VT. This is the analyte volume plus the titrant volume. This is the total volume in the solution, right? And this is how far above you've gone. So this is a dilution factor for CT, right? And once you get CT, and you calculate CA, right? And you can say A here may be equal, in this case, to KSP over T. And in this case, it'd be, in this case, it would be T squared. Right? So, now the third one is VE, right? And at VE, then we just use KSP. Right? Because, oops, because at that point, we have added just as many moles of titrant as we have analyte. Okay, so this is the case where you'd say Hg2 plus times iodate minus equals KSP, and that will equal X, oops, that's squared, right? Times 2X squared, right? That's going to be 4X squared, where X is, say, the mercury ion concentration, right? And KSP is whatever it is, right? So in this case, there's no volume in the equation at all. It's just this equivalence, or this equilibrium expression. So somebody say something. I'm super, oh my God, man. No one can see me. Oh, I'm sorry. My papers covered up my camera and I disappeared into the lawn. I'm like an ant. I live in the lawn.
Somebody's The Bug's Life.
I'm like in A Bug's Life. Thank you for, I'm getting so damn old that I don't know who knows anything anymore, right? Bug's Life, those were like 20 years ago. Thank you, Jorge. Someone is alive out there. Henry almost, oh, Alex is going to be a beautiful butterfly. And Elvin laughs. I like it. Okay, cool. Okay, so why don't I get on and actually do a problem using all this stuff that we've blabbed on about here. So I've got so many examples. I'm not going to get to them all today, but I'll make copies of them and give them out to y'all. So, and I'll make even copies of some of the notes because they're actually a little bit better as notes. So, all right. So, here, let's try this one. Let's say that we have a 25.00 milliliters of 0.0864 molar sodium iodide, and we're going to titrate with 0.05 molar silver nitrate. Right? And in this case, Ag plus I minus makes AgI solid 1-to-1. KSP here is equal to 8.3 times 10 to the minus 17, right? So before VE, we're going to do one calculation at 37.00 mils, right? And at that point, our analyte concentration will be VE minus VT over VE, the fraction remaining, times CA times VA over VA plus VT, right? And then, so that's how we're going to calculate that first one. So, and then we're going to need to know VE though. So VE times the CT, right, should equal VE times CA, right, will equal equivalence volume is the volume of titrate. Right. So VE times CT is equal to VA times CA. That's the equivalence volume. And there can be a stoichiometric factor there. In this case, it's 1 to 1 to 1. So there's no stoichiometric factor there. And let's see here. So we have got VE here will equal VA times CA over CT will equal 25 milliliters times, now CA over CT, I can do those in millimoles per milliliter, right? Molar is moles per liter or millimoles per milliliter. It's the same unit, right? This is going to be 0.08640 over 0.05150. Right? And that is equal to
41.94.
41.94. Excellent.
Yes, sir.
Thank you. Alvin. Suddenly the computer bursts to life. And Alvin's silver tongue speaks to me. Thank you, Alvin. It's just so shocking. It's just so shocking. I'm just talking to myself here. I'm going crazy. Okay, milliliters. Right, that number of milliliters, right? and now, so this is VE, right? So now we can do the A calculation, the analyte concentration, which is equal to the the iodide concentration, which is going to equal this expression up here, right? So VE is going to be 41.94 minus VT, 37, all over VE, right? Times 0.08640 is CA, and then times VA, which is 25. No. At 25 over 25 plus 37. These are all 4 sig figs here, right? So in my calculations, give me here that I minus equals 0.004. Yes? Yes,
Yes,
Alvin?
sir. Yep.
What is it?
0.00410.
410. And then a little 5, a subscript 5. I love it. Great. Okay, so this is what we're doing here. Oh, you guys can barely see that, right? So this is before endpoint. Then let's do the after one. And at the after endpoint, right, we have this is at 46.10 milliliters. VT is equal to 46.10 mLs, right? And let's see here. In that case, we've got the, now we're going to calculate the titrant concentration, right? So CT, well, no, it's actually not called CT. This is called AG plus, right? CT is the original titrant concentration, right? So now we'll just call it AG plus because we need a different symbol. Right, so that's going to be 0.0515. Oh, that's the original. Then 46.10 minus 41.94, right? 46 minus 41. That's the amount, the number of mils past the endpoint that we went. Divide that by the total volume, 25.00. That's the original, plus the amount of titrant that we added, which is 46.10, right? And this gives us, oh God, 0.003013. Is that right, Alan?
Yes, sir.
Excellent. Cool. So now we have AGI. So now we got the AG plus concentration, right? So now we want the I minus concentration. Now at this point, basically what we have is we have this volume and it's full of I minus, right? From sodium iodide. And we've added Ag plus so that we've completely titrated, we've completely collapsed all of the iodide into a solid. Now we're adding excess silver, right? Now, there is a lie there, right? Which is we know that there's always some equilibrium saying, well, there's some Ag plus and some I minus in solution, right? The Ag plus is mainly coming from, solution is mainly coming from the silver nitrate that we're adding, right? So there's a bunch of Ag plus in the solution. We already calculated this. The I minus is coming from the dissolution here. The I minus is super darn small because the KSP is super darn small. Therefore, we're going to calculate it using KSP, right? That is going to equal the KSP over AG plus, which is going to equal 8.3 times 10 to the minus 17 divided by the 0.003013, which should equal something really super small.
2.75 times 10 to the power negative 14.
2.75 times 10 to the minus 14, right? Excellent. And then, so the PAG is the negative log of this value, which is equal to what, Calvin?
13.56.
13.56. Excellent. Wait. No, the PI. Sorry, the PI. Ah, we've got excess iodine. Hi, this is iodine. This is the iodide. Right? And the PI is the negative log of that is 13.56. Oh my gosh. Okay, so 13.56. In this case, this number basically, this is a log, so we don't count these guys as sig figs. These guys are sig figs, and these guys come from, oops, I'm missing one. Because there's 3 sig figs here, right? 2.75. No, there's only 2. There's only 2. This is 8.3, so this is correct. 13.56. Good. Ah, okay. So now let's do the VE calculation. Wait, I'm moving too quickly here. Taking it away right as soon as I finish it. How am I doing? Is this totally boring ass shit? Somebody say yes. 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 This is the most boring crap on the planet. You guys are going to get it somehow. So, I mean, it's just all tricks. You know, you got to know these stupid ass tricks to be a chemist sometimes, you know? You got to work your way through all this nonsense. Ah. Okay. So, let's see here. Let's do the calculation at VE. Let's say at VE, the equivalence volume at this hypothetical point here, VE, then we have AG plus times I minus is equal to KSP, right? And then so, I forget what we're looking for, I minus. They're the same, right? So AG plus equals I minus equals, the square root of KSP, right? Which is equal to square root of 8.3 10 to the minus 17, and that is 9.11 times 10 to the minus 9. It's carrying extra sig fig here. And so the PAG is equal to negative log of that minus log of 9.11 times 10 to the minus 9 is equal to 8.04. So anyway, so there's 2 sig figs here because, there actually should be another digit in this thing. I don't know if this 0 is significant. I'm going to have to check in on that.
No, that 0 is significant. It's in the middle of the 2 numbers, so it is significant.
But yeah, I guess you're right. Yep.
Trailing zeros and those zeros are significant.
I know that. It's just like when you separate them like into the mantissa and the exponent,
Yeah, they are.
you know, I'm not really sure. I think you're probably right.
I'm positive.
Oh God. Okay. So, alrighty. So that is one example here done. Let's do another example. How about let's do one of the homework problems from chapter 7. Chapter 7. Is that what does that do? Geez, I'm so sorry. I should know that. What does chapter 7 do here? Let me check this out. Does anybody know?
I don't know.
Let's see here. Chapter 7. Oh, it's due December 3rd. Holy crap. You guys got a lot of time. Okay, so I'm just going to go ahead and do these homework problems then. Okay. Because I'm just sick of the notes, so let me just do the homework. So you guys are lucking out, man. There's only 18 problems, and I'm going to do a couple of them today, right? So, this is the zinc-containing ore. Ore problem. Okay, so we've got some zinc-containing ore, right? And we're going to assume, let's make an assumption. We always have them, right? Let's assume that the only reaction with H plus that consumes H plus is zinc plus 2H plus makes zinc 2 plus H2. Right, so zinc is going to react with HCl and make zinc 2 and H2. Right? So if you actually had a rock like this or a bunch of sand or something, you know, this might not be a bad place to start because there are very few reduced metals in nature, you know, and very few of them react with H plus to make hydrogen gas. You know? So if we were to take this and take, let's say we had a specimen size of, let's see, how much of this we have? This is 1.720 grams of this stuff, right? This is our zinc ore. Then what we're going to add to this, add to the beaker, 150 mils of 0.6 molar HCl. All right. And then we'll just add enough water to make this 300 milliliters here, right? Actually, this is a 3 sig fig problem, so it's just 300 mils, right? So, and what happens when we did this is we got some H2, right? You know, and we stir it for a good while. We let it react fully, right? And then we have excess HCl. right? This is the key here. And so in order to determine how much zinc reacted, we need to know how much HCl is left over, right? So there's this much zinc, let's say, and then we put in this much HCl, right? And then what we did was we did a titration to measure the excess HCl. And then so we know the total, right? This is excess. And so the total minus the excess is equal to the amount of zinc, sort of like the equivalent electrons from the zinc, right? What am I doing here? Making sense? Okay.
Can you move it?
Sorry?
Can you please move the paper a little bit to the right?
To the right? Yeah.
There you go. Yeah, thank you.
Oh, wow. Okay, cool. Because I show, on my screen, it's like got a bunch of stuff on the sides. That's okay, cool. So, let's just get some deets here. It took 9.12 milliliters of 0.511 molar NaOH to titrate, excess H plus. So this basically tells us how many moles of excess H plus we had, right? It's going to be this times this, right? So let's say that so the excess. Oh, I see. Actually, there's an interesting caveat here, is that we aliquoted 20 mLs of the supernatant, right? Just 20 mLs of it. And there's 300 mLs total there, right? And then that took 9 mils of 0.511, right? So in this 20 mils, the excess H plus is 9.12 milliliters times 0.511 millimoles per milliliter of OH times 1 H plus for 1 OH minus, right? So this guy is equal to, oh shoot, I totally didn't write that down exactly. This is
4.66.
4.66 millimoles. There we go. Right. But then in order to get this scaled up to the total amount, right, we want to multiply by 300 mLs over 20.0 mLs. So this is the ratio. This is 20 out of 300. So we multiply this through, then this guy here is
69.
69, exactly, 69.9. This is millimoles of H plus, right? So this guy here is 69.9 millimoles. You can see that, right? Excellent.
Still a little bit to the right, maybe.
Oh, really? What?
No, to the, I mean, that will be your left then. Yes, more.
The left right or the right?
You're going.
I'm just joking around.
You're going to the right one. Yeah. Yeah. There you go.
Okay. So let's see. So the millimoles of zinc consumed here, right? Or let's say the millimoles of H plus used in the zinc titration or reaction really is let's see, it's going to be this total amount minus this excess amount, so it's going to be 150 mLs times 0.600 moles per ml minus 69.9 moles of H plus, right? So this guy here that's about
20.1.
20.1 millimoles, right? And now to get the amount of zinc in here, right, we're going to say 20.1 millimoles of H plus times 1 zinc for 2 H plus, right? And then multiply by the formula weight of zinc, which is 16, wait, what's the formula weight of 65.38. And this guy here should give us
657.06.
657.06 milligrams of zinc, right? So I'm just going to say, milligrams per millimole here, right? Millimoles of H plus. So this is going to give us 657 milligrams, right? And then if we want to then calculate the fraction of the original ore, we had 1720 milligrams. It was 1.720 grams. Multiply that by 1,000, we get 1720 milligrams. So the percent zinc is going to be 657 over 1720 times 100. Oops. Equals
38.19.
38.2.
20. Yes, that's correct. Sorry.
Yeah, 38.2. We did it. Oh my God. Now we have 4 minutes left, which I plan to waste completely. You guys can apply for your tuition refund here. No, how do we do this? Let me see if I have anything interesting to tell you about this process. We really don't have time to do any other problems here, I don't think. Okay, well, let's. Oh, okay. We can set one up here. We can set this one up. So we have this is another problem here where we have 88.0 milliliters of 0.150 molar NaCl, and we have 14.0 milliliters of 0.225 molar CaCl2, right? And we're going to ask the question, how many milliliters of 0.1818 molar AgNO3 will just react with the above? We'll titrate the above. Chloride, right? So in order to do this, we're just going to calculate the total moles of, or millimoles of chloride from these guys, right? So it's 88.0 times 0.15 times 1 chloride plus 14.0 times 0.225 times 2 chlorides for CaCl2, right? Add these guys up, we get 19.5 millimoles of chloride, right? And now VE, right, is going to be 19.5 millimoles of chloride divided by 0.1818 millimoles of silver per milliliter. This guy here will equal 107.26. 26 is not significant. mL, so it's Ag. Boom. Done. Perfectly on time. This is my mic. I just dropped it. Does that make me cool? Oh, yeah. Let's see. Hold on. Am I forgetting anything super important that I should know as a teacher? That I should be teaching you some stuff? When is our last exam? Our last exam is our final exam. We have our final exam on, let's see here. It is 7:15 a.m. Holy crap. On December the 14th. Merry Christmas, everyone. This is our final.
Thank you, Dr. Terrell. You too.
Oh, thank you. Alex says GLHF. I do not even want to know what that means. Yes, I do. What am I saying? GLHF. Who knows what that means? Somebody privately messaged me what that. Oh, good luck, have fun. Oh, okay, all right. Great. Thank you. Okay, guys. Bye-bye. Have a good one.